Welcome to ePathshala lecture series on computer science. In this module on data analytics, we will be discussing about support vector machines, which is part of the data analysis and foundations to it. The objective of this module are: first, we will be learning the basics of linearly separable problems and understand how support vector machine may be used for solving a linearly separable problem. Finally, we will be learning about various support vector machine implementations and its applications in the field of computer science environment. So, to start with, let us first understand the idea behind SVM. So, this will provide you a complete picture of what exactly is a support vector machine. Suppose we are given with a set of data points which belongs to, say, two classes. So, the data points should belong to either to one of the class. So, either it must belong to the first class or to the second class. The objective here is to find an optimal plane, in other words an optimal hyperplane that separates the data. So, here we are trying to come up with an optimal hyperplane that will help us in clearly distinguishing between data points related to class 1 and data points related to class 2. So, the objectives of SVM here are to maximize the distance. Suppose you have an hyperplane with which you can clearly distinguish between one class of data and another class of data, means then the margin between these two data must be maximum. Only then we can conclude that the hyperplane which is defined by means of the support vector machine or the support vectors is optimal. And secondly, we need to minimize the risk of misclassifying, because in real scenarios when we are dealing with data, we may not end up with, say, a clear cut classification. There are certain scenarios where some points may be misclassified. So, the second objective must be to minimize the risk of misclassification. Now, when misclassification may come into picture is, suppose a particular instance is not part of your training data, or suppose an unseen test sample is being used. So, for such scenarios we will have to avoid the problem of misclassification. So, the approach here is we are going to formulate a constraint based optimization problem, which is then going to be solved by means of quadratic programming. So, this provides a complete idea about what exactly is SVM. So, to summarize, SVM is going to provide a hyperplane which may be useful for clearly distinguishing between one type of data which belongs to, say, one class and the other type of data belonging to the second class. Let us analyze this support vector machine in detail with few diagrams. Now, in this diagram you may find two sets of data. Practically speaking, they are one data set. In that data set, few data, say shown in green shades, is associated to one class label, and the other data set represented by white color ellipse is associated to second class label. So, now what is that we are trying to do with the help of support vector machine methodology is, we are trying to find a linear hyperplane, or it can be considered even as a decision boundary. This decision boundary will help in separating the data. So, one possible solution is, say, the line indicated by the red line. Now, this straight line will clearly help to understand that the set of data in green shades is belonging to one type, and the set of data in white elliptical shade is associated to another type. But when we take a closer look at the data, we can also end up with another possible solution, say the dashed line indicated by the notation B2. So, in the previous scenario we got one straight line that provides a clear demarcation. Similarly, we also end up with another possible solution. But if we analyze further, we may find some more possible solutions, like the dashed lines indicated in this diagram. So, line number 2, 3, 4, 5, 6. So, these are the various other possible solutions or decision boundaries or linear hyperplanes which may be used for clearly demarcating between the data given in a data set based on their class labels. But among all these linear boundaries, we need to identify which one is better, or in other words we need to identify which one is optimal. Take for example, here in this diagram we have two boundaries, decision boundaries indicated by boundary 1 and boundary 2. Now we will have to decide among these two boundaries which one is better, whether B1 or B2. Now how can we define this better? That actually is done using the support vectors. Let us understand what is support vector through this session. Before that, we need to understand how we can decide a boundary is better. So when we are considering the boundary to be the best solution, then we will have to identify, say, the margin. Now what exactly this margin represents and how this margin may be used for determining a particular boundary is better or not. Now take the line B1, the decision boundary B1. Now this decision boundary B1 is associated to the two datas by means of its distance with respect to the last or the data point which is nearest to this boundary line in either case. Take this set of data, that is the data represented by white circles. The data point which is very near to the decision boundary B1 is this data. Now this data will act as, say, a point which is going to decide the margin for the boundary line B1. Similarly, take the next set of data represented using green shade. Among this data, we may find this particular data which is going to be very near to the decision boundary B1. So now we can consider this data and this green shaded data to be the nearest data points to this decision boundary B1. Now based on these two nearest boundary points, we can now define a margin for this decision boundary B1. So now the width of this or the distance between these two boundaries is considered to be the margin. Similarly, for the second decision boundary B2, we may find this circle as the nearest point in this data and this square green shaded data is nearest to the boundary B2. Therefore, now we can make use of this green data and this white shaded data for deciding or defining the boundary for the line or the hyperplane B2. Now when you take a look at these two decision boundaries B1 and B2, B1 has got a larger margin when compared with the B2 line. So now what we can do is, we can clearly say the boundary with larger margin may be considered as the best solution. The reason is, when the margin is large, we have enough of space between these two sets of data. Therefore, we can clearly state this line, that is B1 boundary line or decision boundary, may be apt for providing a clear demarcation between class 1 data and class 2 data. But when you consider B2, this decision boundary does not have a larger margin. Therefore, we cannot consider this to be a better solution or a better hyperplane or a better decision boundary for distinguishing between class 1 type data and class 2 type data. So ultimately, we are trying to define a hyperplane that maximizes the margin. So now when we are trying to maximize the margin, how exactly SVM is taking a look at this solution? SVM actually maximizes the margin around the separating hyperplane. So in the previous line, we found this B1 is going to be the separating hyperplane and we are trying to maximize this margin. And secondly, the decision function is fully specified by a subset of training sample which is nothing but the support vectors. So in the diagram, we have decision samples, say the point which is in white circle and the point green shaded point. These two I told it is going to decide the decision boundary. Okay. So these two data points are treated to be the support decision points. So with the help of these two support decision points, we are going to decide the margin. So support vector machine ultimately maximizes the margin which is around the separating hyperplane, and this is decided completely based on a subset of training sample which is called as support vectors. In general, how we can define SVM? So in general, SVM is associated to, say, an input set and an output set. The input set is going to have the input and the output. Here the output can be, say, the class labels. So we have input which is nothing but training pairs. So when we provide input to the SVM methodology or technique, it is going to take set of sample features as an input. The feature set can be n in number. So, I may have x1 till xn indicating n number of features for the input data. Now, with this input data, what is that we are going to do is, that is with the set of input features, we are going to identify say a particular feature that may be important for providing a clear demarcation between class 1 type of input data and class 2 type of input data. So, provided the input, what will be the output? The output is going to be a set of weight or weights which indicates a weightage to a feature, and it is this feature which may help in predicting the value for y. So, now y may be say the class label which we are trying to predict for a given data, and this class label will be decided based on the weights associated to a set of input features, and these input features are going to be considered to be key features. So, what is the important difference with respect to say the rest of the environment is, when we are trying to work with respect to SVM, it is fundamentally an optimization problem, and here what is that we are trying to optimize is, we are trying to optimize the margin, that is we are trying to identify an optimal margin. Here the optimal margin is going to be a maximum margin. Now, this optimal margin is going to help in reducing the number of weights. So, originally we may be having n number of features. From the set of n features, we are going to derive a subset of features, and for that subset only we are going to identify weights. So, these weights which are going to be non-zero, it is going to associate to a limited set of features from your input feature set. So, here these non-zero weights actually correspond to the support vectors which is going to be part of your training sample, and since it is going to support the separating hyperplane, it is called as a support vector. So, in general you are going to have set of input and output for the data which is called as the training sample. This training sample will be provided to the support vector machine. The support vector machine will generate set of weights which may be associated to a set of special features. These special features will be used for the purpose of clear demarcation of the data sets. So, in this diagram we have a hyperplane H0 that is decided based on two other boundaries which is indicated by the notation H1 and H2. So, for this given diagram, we define two planes which is H1 and H2 respectively. So, how H1 and H2 may be represented mathematically is, H1 may be decided based on the weight W associated to the input feature x, the input ith x feature xi plus say a bias factor b which is equal to +1, and the second hyperplane H2 may be decided based on this equation, formal equation W into x I plus b which is equal to -1. So, here the +1 and -1 indicates whether the data is part of say the first class label or whether the data is associated to the second class label. Putting together this H1 and H2 together may be used for deciding the separating boundary or the decision boundary H0, which in general is called as the median for this H1 and H2, may be defined mathematically using the equation W into xi plus b is equal to 0. Here from this diagram we can see there are two notations d plus and d minus. Here d plus is the shortest distance to the closest positive point. In other words, from the set of data that is associated to one type of class or class label, we identify a point that is very close to the hyperplane H0 or the median plane H0, and d minus is that distance that indicates the distance between say the closest point in the other set of data with respect to the hyperplane H0. So, from the other set of data that is associated to the second class label, in this diagram we find say 3 points lying on the hyperplane H2, and these points and their corresponding distance with respect to the median is indicated as d minus. So, now the total margin is going to be the sum of d plus and d minus, so which is indicated as the margin or the gutter of the separating hyperplane. So, it is d plus plus d minus. This total sum of distance is treated to be the margin. Now, formally how we can define this separating hyperplane? Separating hyperplane may be defined using a form of equation as shown here, which is equal to W transpose x plus B equal to 0, where W is the weight vector, x is the input vector and B is the bias. And also we can write this in two forms indicating the two types of data associated to two types of class labels. If this equation's value is greater than equal to 0, then it is associated to the positive data, else it is going to be associated to the negative data. So, here positive and negative, what I mean is the two types of class labels or the two class labels associated to the given data set. There are few more definitions which we need to know before understanding the SVM completely with an example. So, margin of separation, which is indicated as D. So, as I already mentioned, this is nothing but the separating distance between the closest data point and the hyperplane or the median plane. And optimal hyperplane is the maximal margin which a particular hyperplane may exhibit when the margin or the distance between the closest point and the median is going to be maximum. So, we need to understand what exactly is margin of separation and the optimal hyperplane, how it is defined based on the maximum margin. Now, the idea here is we need to identify a hyperplane which can maximize the width or say the margin. So, how are we going to maximize the margin? Suppose we want a linear regression or a linear separator with a big margin, then what is that we need to do is we need to understand few fundamentals about how to calculate the width. Suppose I have a data point say x comma y, and this data point is at a distance with respect to say for example a linear plane or a hyperplane. Assume that line is defined by means of an equation Ax plus By plus C is equal to 0. So, the data point is x naught y naught and the line to which it is associated with respect with a distance is Ax plus By plus C is equal to 0. Now, the distance between this data point x naught y naught and the line is given as A x naught plus B y naught plus C. This is the absolute value of this equation divided by square root of A square plus B square. So, now the distance with respect to a point and the hyperplane is defined by this equation. Therefore, we can now define the distance with respect to h naught and h1. So, the distance with respect to h naught and h1, so here h naught is the median and h1 is the decision boundary associated to a closest point from data related to first class label. So, this equation W into x plus b divided by norm of W, which is equal to 1 by norm of W. This is for one boundary with respect to the median h naught. Similarly, we have another boundary with respect to the median, that is h2 with respect to the median. So, we will be having 2 1 by norm W. So, when we add these two 1 by norm W, we end up with a total distance between the two boundaries, that is h1 and h2. So, thus it is going to be equal to 1 divided by W plus 1 divided by another norm W, which is equal to 2 divided by norm W. Now, we can always define this 2 by W with say this generalized equation margin is equal to 2 divided by W square. Now, practically speaking, we are actually trying to maximize this margin. So, now when we want to maximize this, we need to work with respect to conditions which are indicated by these two equations, and we need to identify data points that satisfy these two equations. So, now when we are actually generalizing this width or the margin with respect to the two boundary lines h1 and h2, how are we getting this value? See, for optimization problem that is presented in this particular module, actually it is very difficult to solve because it depends on the value of W, which is norm W, norm of W. See, this norm of W, as I already mentioned, involves square root. So, what is that we can do is we can actually replace this norm value by means of half of the square of the norm. So, this is for the purpose of convenience. So, now what we can do is we can always replace this W by means of half norm W square. Therefore, we will end up with this value 2 divided by norm of the vector W the whole square. So, here though we change it for convenience, the solution is not going to be affected. So, to understand how do we get this margin as equal to 2 divided by norm of the vector w square, it is this explanation. So, here we want to maximize this margin, which is equivalent to minimizing the inverse of margin. So, when you take the inverse of margin, it is represented as L of w, which is equal to w square divided by 2, and this equation is subjected to the following constraint that may indicate whether the data is going to fall under category 1 or category 2. So, ultimately this is going to be a constraint optimization problem which can be solved by means of quadratic programming. Suppose if the problem is not linearly separable, for example, here we have two boundaries with respect to the median. Now, you find one data point indicated in green shade falls at the other side of the boundary. Similarly, one data point which is of this type falls on the lower side of this boundary. So, now when we have a linear boundary or a hyperplane which is indicated by the red line, does not provide a clear demarcation between the first type of data and the second type of data. Here what I mean by first type of and second type of data is based on the class labels. Then what is that we need to do is, we need to introduce slack variables, because the data points that is violating the boundary conditions will introduce certain errors. So, these errors need to be accounted. So, when we introduce slack variables, of course, we take care of these errors. So, the slack variable is fundamentally indicated by means of this epsilon. So, we are going to take the summation of the slack variables and we are going to use it for maximizing or minimizing the margin equation. So, if it is going to be 2 divided by norm of w square, then we need to maximize. If it is going to be the inverse of margin means, then we need to minimize the inverse value. So, accordingly, either we will be adding this epsilon value, which is nothing but the slack variable. Since we are introducing a slack variable, accordingly the governing equation should also be modified with respect to the slack variable. So, if it is going to be a positive value, we subtract the slack variable, and if it is going to fall under the negative class means, then it will be added with respect to the slack variable. There is another scenario, say in this environment, this is say the scatter diagram for the data point. Now, the dots in red shade and the dots in blue shade indicate the data belonging to class 1 and say the second class. Assume red shades belong to class 1 and blue shade of dots belong to class 2. Now, here we cannot come up with a linear boundary. So, what exactly happens is the decision boundary is not going to be linear. So, if it is not linear, so it will look like this. So, we are not expecting a straight line. If we have a straight line, then we cannot end up with a proper demarcation. In such scenario, what is that we need to do is, we need to transform the data into a high dimensional space. So, when we transform that into a high dimensional space, naturally the decision boundary becomes a bit linear, and accordingly we may end up with proper decision boundary which demarcates class 1 type of data and class 2 type of data. Now, how this transformation may be done? Say, take a look at this diagram. Here we have a decision boundary that is not going to be linear in nature. So, what we are going to do is, we are going to apply a transformation over the given data. So, the transformation is defined by means of say this notation phi. So, apply the transformation on the data which is available in this diagram. So, we apply transformation for the data which is represented by O, and also transformation of the data which is represented by X. So, transformation of O and transformation of X. Now, when you transform, the data gets transformed into a higher dimensional space, and hence we can end up with a proper decision boundary for demarcating these two types of data. So, what exactly we are trying to do here is, we are trying to work with respect to a non-linear support vector machine. So, for example, if we have say a data determined by this characteristic equation x minus a multiplied by x minus b, we may not end up, or we cannot separate this data by means of a linear function. Therefore, we need to transform that into another space, a high dimensional space, and then we can perform the linear separation. So, we can separate the data and solve it by means of a quadratic equation. So, if we rearrange the equation like this, x square minus a plus b of x plus ab, then it becomes a quadratic equation. Once we end up with a quadratic equation, of course we can gain a linear separation, and this data which is associated with this nonlinear boundary now may be decided by means of a linear boundary like this. Now, how this transformation can happen? For this we need to know about kernels. So, a linear classifier, practically speaking, relies greatly on the dot product between the vectors. So, if xi and xj are two features, then we need to depend on the dot products between these two vectors xi and xj. So, k of xi xj is equal to xi transpose multiplied by xj, and if every data point is going to be mapped to a high dimensional space using some transformation, the same equation when you apply the function phi, it may look like this. So, k of xij will be equal to transformation of xi and transformation of xj, this product together. So, what exactly this kernel is and why it is used in SVM is, kernel is actually going to be a function that corresponds to an inner product in some expanded feature space. So, given the feature set, kernel function will help in identifying the inner product of this feature space in some expanded dimension. There are few examples for kernel functions. So, kernel functions can be linear, it can be polynomial in nature, it can be Gaussian in nature, or it can be sigmoid. Few of the example kernel functions are given here. So, what is so important about this SVM? What is the advantage of SVM? Normally, when we are dealing with respect to kernel functions, they require calculations only with respect to the data points and their associated dimensions. So, when you have a data x, then this must be associated to the dimension d. Rd is nothing but the record related to the dimension d. So, we need to just determine which kernel function may be associated here. So, what normally we do is we try to identify this by means of a trial and error method only. So, the advantage being here is all that we need to worry about is only about the trade-off parameter c and which particular kernel function are we going to make use of it. The support vector machine, when compared with linear regression, how it may? Say for example, when you have a data set like this, what exactly we may expect out is, we may expect out say a linear hyperplane like this. But when you apply linear regression, actually speaking, it may provide you a straight line, but the straight line may not provide you proper decision making. The reason is, here from this diagram you can find scatter plot, you can find few of the data belonging to say green shade, assume it is associated to one class, also falls above this boundary line. So, what exactly we expect here is, we expect say a curve like this or a decision boundary like this, which may help in providing clear demarcation of this data. So, when we apply a linear regression, we may end up with such kind of straight line, but if we apply SVM, we end up with such a decision boundary that provides a clear demarcation between the two types of data. So, the real power of SVM is, suppose if we have a data set like this, then only SVM is said to provide say an effective result. So, when we apply the training samples and when we train it properly, we may end up with a clear demarcation or a decision boundary as shown here. But if the training samples and the training is not happening properly, sometimes SVM may end up with such kind of decision boundaries. So, here you may find one data point related to one particular decision boundary. Similarly, few of the outliers of the data set belonging to the red shade is associated to different decision boundaries. So, this is also going to be actually a drawback. So, the idea here is training is very important with respect to the support vector machine. So, what are the various forms of implementation of SVM are? There are SVM Lite, SVM Struct, SVM Lib, then MySVM, SVM MATLAB is available, then you have Hiller. These are the various implementations that are currently available over the web for the purpose of classifying data. So, what are the various places in which SVM may be applied are, SVM is very useful with respect to text and hypertext categorization, because when you are dealing with categorical label, of course, the categorical label need to be converted into some form of numerical value, and then when you are dealing with a numerical value, we of course need to have a proper decision boundary. So, SVM works out fine for text data. Then for classification of images, then in medical domain SVMs are widely applied, and also with respect to handwritten characters, recognizing handwritten characters and predicting what character or word it may be is perfectly done by means of SVM. These are all few of the applications to be mentioned here, but there are lot more. So, to summarize, in this module we discussed about how SVM may be used for deciding which data belongs to which particular class label. So, ultimately what we are trying to do is, we are trying to make use of a learning methodology based on a mathematical technique which will make or which will utilize the rich theory of optimization. Secondly, we discussed about how kernels may help SVM for working with respect to a problem which is not linearly separable. And finally, we also discussed how SVM is extremely successful and robust with respect to different types of application, and how they may be used for the purpose of generalizing the problem as well. Thank you.